On the last week, we finished the topics connected with quite abstract mathematical apparatus of quantum mechanics. And now we are ready to go further and discuss some really interesting physical phenomena and their applications. In this lesson, we will give a talk on the phenomenon of quantum entanglement, which acts as a cornerstone for all quantum computations. In order to understand what the entangled state is, for the sake of simplicity, we'll consider only pure entangled states. We recall our first formal definition. If one has a physical system of several qubits being in pure states, and the system's state vector cannot be represented as a tensor product of each qubit's state vectors, then such state is called inseparable or entangled. Let us now consider a very representative example of two qubits entangled states. For certain historical reason we touch on later, these states are being called the Bell states, or the EPR pairs. Such states are the case of interest for us, since they act as a resource for superdense coding and quantum teleportation. There are 4 Bell states, and you can see all of them on the slide. These Bell states are beta sub 00, beta sub 01, beta sub 10, and beta sub 11. Let's take a closer look at them. It's not hard to see that they are somehow different one from each other. For example, the state beta 11 differs from the state beta 01 in its sign, or relative phase. Similarly, the state beta 10 differs from the state beta 00. The states beta 00 and beta 01 have different quantum states of second qubit. The states beta 10 and beta 11 are also different from each other in the second qubit states. It is sometimes referred to as parity difference. Let us note that, in fact, the relative phase and the parity define each of the Bell states. In order to describe these 4 Bell states, one needs 2 classical bits. The latter can be reversed. One needs 2 bits to describe a Bell state, but it also means that one can transfer 2 bits of information within that Bell state. Later, we will discuss it extensively. Let us now consider in more detail one of these states, for example, beta 11. Imagine the following thought experiment. Let there be a pair of fermions with a spin projection of 1/2 prepared in the state beta 11. The particles could be electrons or parts of a certain molecule. One of the real experiments was set in 1976 in Saclay, a suburb of Paris, and included a pair of protons being prepared in the Bell state. Once the protons were released from an accelerator, they scattered on a hydrogen target. Now suppose our particles in state beta 11 move in the opposite directions. To be definite, we will call a particle moving to the left an A particle, and the one moving to right a B particle. We'll mark a state of a plus 1/2 spin z-axis projection with 0, and understand a state 1 as a state with minus 1/2 spin projection. The states 0 and 1 on the picture correspond to up and down arrows respectively. So, the first term in the beta 11 superposition means that the particle A is in the 0 state and has the plus 1/2 spin projection arrow up, whereas the particle B is in the state 1 and has the spin projection of minus 1/2 arrow down. In this second term, the particles have the places swapped. Now the particle A is in the state 1 and have plus minus 1/2 spin projection arrow down, while the B particle is in the state 0 and have the spin projection of plus 1/2 arrow up. Let us remark that the choice of notation is a matter of convenience and had no further effect. In our thought experiment, we will measure the spin projection of particle A with a Stern-Gerlach instrument. If particle A tilts to the top after passing the instrument, it has the spin projection of plus 1/2, and the first term in beta 11 superposition realizes. Thus, after such collapse, particle A is brought to the state 0. It means that the B particle with 100% probability will be in a state 1. So, if one passes that B particle through another Stern-Gerlach instrument, such particle will tilt to the down, confirming the fact that it is in the state 1. If the particle A tilts to the down, as it is shown on the figure, then the particle B after the collapse will turn up to be in the state 1. We see that since our system is prepared in the Bell state beta 11 and we have the spin projection of A particle measured, then there is no need for us to measure the spin projection of the B particle in order to find out its quantum state. The quantum states of these two particles appear to be definitely interconnected, i.e. there are certain correlations between them. In the particular case of the Bell state beta 11, the state of A and B particles were anticorrelated, since the spin projection values always appear to be opposite to each other. So if one particle had the spin of projection of +1/2, then the second one had the spin projection of -1/2. Similarly, one could set an analogous experiment up for a system prepared in another Bell state. In all this experiment, one will observe correlations between particle states. So, the Bell states are pure entangled quantum states of a physical system. Moreover, the Bell states are the most entangled states possible for a system of 2 qubits. This means that if one takes a partial trace over the states of qubit B from the density matrix of the 2-qubit system A plus B, then one obtains a density matrix for A qubit being equal to unit matrix multiplied by a constant. We recall that the density matrix of a pure state is just a projection on that state. For instance, let us consider the same state beta 11. So, we have a density matrix ρ AB, which is a projection on the state beta 11. Let's use the definition of the beta 11 and rewrite this. 1/2, 0,1 minus 1,0 and bra 0,1 minus 1,0. Now we can open the brackets. This equals to 1/2 ket 1,0 0,1 0,1 minus 0,1 1,0 minus 1,0 0,1 and plus 1,0 1,0. So now I take the partial trace from ρ AB over the states of the qubit B. Partial trace ρ AB, by definition, it's equal identity I tensor multiplied to the 0 state of a qubit B. Here we got ρ AB and again identical A tensor multiplied by 0 state B. And the second term plus 1A tensor 1B ρ AB identity matrix for A and the state 1 for the qubit B. This is just the definition of a partial trace. Let's consider the obtained terms in more detail. The partial trace operation is linear, and that's why each one of these 2 terms falls apart into 4 terms formed by these terms. Let's take a closer look at the term that contains this construction. It has the form 1A tensor multiplied by 0B, 0A, 1B, 1A, 0B, and again identity I, A, tensor by 0b. So this is just the term we are considering now. And these two guys, they are from the definition of a partial trace. This thing is actually the tensor product of 0a and 1b. And we can use the identity A and apply it to the state 0a. It wouldn't change anything, and we can make the same procedure here. We can apply the identity A to the state 1a. It also wouldn't change anything. That's why the thing equals 0b, 0a multiplied by 1b, bra 1a, 0b. And again, 0b. And we can now swap these two terms, these two multipliers. And what we'll see now, we'll have 1b here, and we'll have 0a here. The thing is, now we can combine these two terms into a scalar product of the orthogonal states 0b and 1b, which is equal to 0. And thus, the whole thing will be equal to 0. It can be shown in the same way that the terms 0, 1 and 1, 0 and 1, 0, 0, 1 actually don't matter, because they will give us 0 in these both terms. However, the two other terms, 1, 0, 1, 0 and 0, 1, 0, 1, will yield some results that, after all, will lead us to the final result 1/2 identity A. And this is our answer. Finally, we obtain the qubit A density matrix to be the product of the unit matrix and constant. The situation is the same for any other Bell state. Equivalently, the density matrix in this is the sum of projections 0, 0 and 1, 1 with coefficients of 1/2. These coefficients act like possibilities to find the A qubit in the corresponding basis state. Thus, the qubit A will turn up in the state 0 in half of the experiments and in the state 1 in another half of experiments. A similar result can also be obtained for the qubit B. So, the results of such local measurement will be absolutely random. Let us remark that 4 Bell states form an orthogonal basis for the Hilbert space of 2 qubits. This means that any state vector of the 2 qubits quantum system can be represented in the form of Bell state superposition. Since the Bell states are orthonormal and form a basis, they are macroscopically distinguishable. In other words, if one is able to perform a measurement procedure for both qubits A and B, so that the state of B qubit is taken into account when measuring the state of A qubit, then one can find out which one of the Bell state was prepared. These jointed measurements are called the Bell measurements, or the measurements in the Bell basis. The setup for such an experiment is presented on the slide. It is unclear for us now, but it is here just in order to show that such an experiment exists. We will get back to it later when discussing superdense coding and quantum teleportation. We shall stress that all entangled state possesses some specific correlations. These correlations do not have analogies in classical physics and have a so-called property of non-locality. This means that the entangled particles can be distanced far away from each other, but the correlations will still exist and manifest themselves in physical experiments. Cautiously, we note that no locality is one of the fundamental scientific problems, and apparently still does not have a finalized formulation. Now, the entangled states, and in particular the Bell states, are widely being used in quantum informatics and telecommunications. However, when they were first discovered, the Bell states acted as the driver for the critique of basics of quantum mechanics. That's why the Bell states we considered are sometimes referred to as EPR pairs. The letters EPR are the first letters of the Einstein, Podolsky, and Rosen surnames. This man formulated a well-known paradox that questions the quantum mechanics postulates. In our next lesson, we will discuss the Einstein-Podolsky paradox, or the EPR paradox, in detail, and consider the hidden variables conception that was offered as an alternative to quantum theory. Thank you for your attention.